In this video, we're going to talk about differential equations which are not homogeneous. So differential equations where on the right-hand side of the equation, we don't just have 0, but we potentially have some function of x. We're going to introduce some terminology today, and then we're going to introduce a couple of theorems that we're going to use over the course of the next several days to help us to construct solutions to non-homogeneous ODEs, sort of one piece at a time, similar to what we've done with homogeneous ODEs. So an ODE is called linear non-homogeneous, or just non-homogeneous for short, if it has the form function of x times the nth derivative of y plus function of x times the n minus 1 derivative of y plus blah 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 all the way down to the first derivative and the 0th derivative. The only difference between the homogeneous equations that we have done and the non-homogeneous equations that we're doing now is that we are going to have some function of x over here on the far right side. For example, the differential equation that we gave for a deflection of the beam, EI times the fourth derivative of y equals the load at the location x, would be an example of a non-homogeneous linear ODE. In this case, the function on the far right side is the one that represents the weight on the beam at the position called x. For a more abstract example, I could give you something like y double prime plus 3y prime plus 4y is equal to maybe e to the 5x plus x squared. In this case, this would be non-homogeneous because on the right-hand side of the equation, instead of 0, we have e to the 5x plus x squared. Now, anytime you're working with an ODE that is not homogeneous, there is an associated ODE which is homogeneous. The ODE that you get if you just took that function on the right-hand side and replaced it with a 0. The homogeneous ODE that you get when you take a non-homogeneous ODE and just set the right-hand side equal to 0, this is called the complementary equation. For example, if I took the ODE y double prime minus 2y prime plus y equals 3x, then the complementary equation would be y double prime minus 2y prime plus y equals 0. Just get rid of 3x and put 0 in its place. Now, in addition to that terminology, we have a few other pieces of terminology that we're going to need in order to converse about non-homogeneous differential equations. Particular solution. A particular solution is one solution to the non-homogeneous ODE. It's not a description of all possible solutions, it's just one solution that you happen to stumble upon somehow. Usually this is denoted by y sub p, p for particular. A complementary solution is a solution not to the ODE that you're working with, but a solution to the complementary equation. A solution to the homogeneous ODE that you would get if you replaced the function on the right-hand side with 0. The complementary function is the description of the general format of all complementary solutions. The complementary function is usually denoted by y sub c, C for complementary. And the general solution is the description of the general format of all particular solutions. The general format of all the solutions to the original non-homogeneous ODE. So when you are solving a non-homogeneous ODE, you're trying to describe all solutions, so you're trying to find the general solution in this language. The general solution is your goal. So if the general solution is all that we care about, why did we introduce all of these other pieces of terminology? The reason is in the following theorem. So you've got a non-homogeneous ODE. You've got a complementary function called y sub c. So you know what the solution to the equation would be if the right-hand side were equal to 0. Then you've got one particular solution. You have one solution to your differential equation where the right-hand side is not equal to 0. Then the general solution of the ODE is given by complementary function plus particular solution. The format of any possible solution to the non-homogeneous ODE is the complementary function plus one particular solution. So here is the big takeaway of this theorem. If you want to solve a non-homogeneous differential equation, you can do it in 3 steps. Step number 1 is to solve the complementary equation. Replace the right side with 0 and use the techniques of the past couple of days to solve the associated homogeneous ODE. Then find just one solution to the non-homogeneous ODE, the one that has the function of x on the right side. Just find one solution. And if you can solve the complementary equation, and find just one solution to the non-homogeneous ODE, then you can solve by adding the functions in step 1 and step 2. This is all that you need to do to solve a non-homogeneous ODE. Solve the complementary equation, find one solution to the non-homogeneous ODE, combine them, and that describes all possible solutions to the non-homogeneous ODE. Let me show you what I mean. So let's go back to our friend y double prime minus 2y prime plus y equals 3x. Let's start by finding the complementary function. Let's start by solving the equation if it had a 0 on the right side. So if I look at that complementary equation, I have y double prime minus 2y prime plus y equals 0, which is homogeneous with constant coefficients. In the case of a homogeneous ODE with constant coefficients, our technique was to guess a solution of the form y equals exponential, e to the rx. Now with that guess, y double prime gets replaced with r squared, y prime gets replaced with r, and y gets replaced with 1. So this becomes r minus 1 equals 0, and r equals positive 1 is a solution of multiplicity 2. So that means that our first solution to the complementary equation is e to the x. Our second solution to the complementary equation is x times e to the x. And therefore our complementary function, the solution to the complementary equation, has the form yc equals c1 e to the x plus c2 x e to the x. Okay, so now we have found the complementary function. We have described all possible solutions to the complementary equation, which is what we get by replacing the right side of the equation with 0. In part B, let's verify that y sub p equals 3x plus 6 is a particular solution. So all I have to do is show that this function solves the original non-homogeneous ODE. So if I calculate y prime, that's equal to 3, and y double prime, that's equal to 0. So if I plug that into my differential equation, then I get 0 minus 2 times y prime plus 1 times y. We would need that to be equal to the 3x, which is on the right-hand side of our original non-homogeneous differential equation. When I simplify that, the plus 6 and the minus 6 cancel out, and I am indeed with the left-hand side that is equal to 3x. Therefore, yes, this one function, 3x plus 6, is a solution, a particular solution to my original non-homogeneous ODE. So now I have the complementary function, and I have one particular solution. And this is all that I need to describe all possible solutions to my differential equation. All possible solutions to my differential equation have the form complementary function plus particular solution. The general solution is c1 e to the x plus c2 x e to the x plus the particular solution 3x plus 6. Every solution to the differential equation must have this format. Let me show you one more time. We have the non-homogeneous ODE, y double prime minus 5y prime plus 6y equals e to the x. Let's start by finding the complementary function. Let's start by solving y double prime minus 5y plus 6y equals 0. Now once again, this is homogeneous with constant coefficients. So I'm going to guess that the solution has the form y equals e to the rx, which gives me the auxiliary equation r squared minus 5r plus 6 equals 0. So in this case, I get two distinct real roots, r equals 2, r equals 3, which gives me two linearly independent solutions that I can combine to get the complementary function. c1 e to the 2x, c2 e to the 3x. So what would a particular solution be? Show that y sub p equals 1/2 e to the x is a particular solution to my non-homogeneous differential equation. Now if I take the first derivative and even the second derivative, the function remains unchanged. So let's go ahead and plug that in to my original non-homogeneous differential equation. Then I get y double prime is 1/2 e to the x minus 5y prime, so minus 5 1/2 e to the x, plus 6 times y, so 6 1/2 e to the x. I would need that to be the function on the right side of my non-homogeneous ODE, which is e to the x. So if I go ahead and simplify that, divide out e to the x, multiply everything through by 2, then this would be equivalent to 1 minus 5 plus 6 equals 2. And that certainly is true. So we have verified that if I set y equal to 1/2 e to the x, then that is one particular solution to my non-homogeneous ODE. So finally, what's the general solution to the differential equation? What do all the solutions to the differential equation look like? They look like the combination of the complementary function and the particular solution that we found in part B. The complementary function was c1 e to the 2x, c2 e to the 3x. And the particular solution that we checked was 1/2 e to the x. Therefore, all the solutions to the differential equation must have this format: complementary function plus particular solution. So in the end, really the only thing that we need to figure out how to do is we need to figure out how to find this particular solution. We already know how to find the complementary function. We can find that using the techniques of the previous couple of days. It's the particular function that we need to figure out how to find. If we can find the particular function, then we can combine that with the complementary function to get the general form of all the solutions to the differential equation. So we're going to spend the next several videos figuring that out. Videos number actually 26 through 31. The next 5 videos are going to be devoted to this question: how do we find one particular solution to a non-homogeneous ODE? That way we can combine it with the complementary function to get the general solution. That concludes today's material. A non-homogeneous ODE just has a function of x on the far right side. Non-homogeneous ODEs can be solved by first solving the complementary equation, the homogeneous ODE that goes with the one that we were given, and then finding one particular solution and combining those.